I'm Chen Juan. Today I'll give you a complete popular science explanation of eigenvalue and eigenvector. The first one is why is eigenvector and eigenvalue so confusing? If you are studying linear algebra and think which concept is the most confusing, many of you think is eigenvalue and eigenvector. Our textbook only says computational method, but often fail to answer some important questions such as why do we study the equation ax equals lambda x and seek the solution? Why is the product of eigenvalue and eigenvector? Why is the product of eigenvalue equals determinant? And what is the meaning of eigenvector and eigenvalue?
So you're gonna give an explanation of all those answers?
Yeah.
Okay, sure. That's maybe this sharing because your answer last time is not satisfied, right?
Mm-hmm.
It's not good enough. So you have this sharing, especially of eigenvalue and eigenvector, right?
Uh-huh.
Okay, next.
No.
So you need to introduce eigenvalue and eigenvector.
Vector.
Yes.
So first, what is the geometry meaning of eigenvalue and eigenvector?
You don't need to write. Yes.
The geometry meaning of eigenvector and eigenvector and eigenvalue is actually quite intuitive. Imagine a matrix A acting on every point at x in space, mapping to a new point ax. If we imagine every point x mapped to ax, we see the entire space transformed. Focus on two lines to the origins. All points on these lines are mapped to points along the same lines.
Also, so what means of among the same line?
Are mapped to I map from here, and then this is v, and then a times v is equal to this.
Is among this direction. Actually, it's only occur scaling and no rotation, right?
And the scaling factor is called lambda, and x is the eigenvalue that doesn't change directions. Third, why is it called eigen? This just means a vector doesn't change directions after transformation. Why is it special, and why is it called eigen? Why is it called eigen? The earliest recognition of eigenvector came from Euler, who found that in rich body rotation, there is always an axis that remains fixed. Lagrange later found that these to be the eigenvector of the inertia matrix. Later, Cauchy named the term characteristic what is that?
I forgot to. Characteristic actually in Italian. Casino. It's not important. Forget it.
Okay. Later, Dave Harvard coined the term eigenvalue from the German root eigen, meaning own yourself.
So this is a historical background, right? Okay, so that was a whole introduction of eigenvalue and eigenvector. Okay, next you're gonna see the detailed explanation of those two of the eigenvalue and eigenvector, right? Okay.
Now let's talk about the second part. the first part is how eigenvalue and eigenvector characterize our matrix tactile space. And now let me characterize our matrix tactile space, describing the feature of the matrix transformation.
Could you give me an example?
Yes.
Because using an example is easy to see. Yes.
Okay. So the example is A equals 2, 1, 0, 3. And then the definition of an eigenvalue and eigenvector is AX equals lambda x. X is the eigenvector and lambda is the eigenvalue. So x is equal to 1, 0 and 1, 1. And lambda is equal to 2 and so any vectors in directions 1, 0 is stretched by factor 2, and any vectors in direction 1, 1 is stretched by factor 3. And so now I want to calculate A times V. And then
what is V?
V is a vector is equal to 2, 1.
What is V?
It is a vector.
Is any vector.
Any vector.
Could it be 3, 1?
Yeah. I'm just taking
Same,
an example.
okay. Right.
And then
you just take an example, you should see that clear.
So 2, 1 is equal to 1, 0 plus 1, 1. So
the question is
so it's A times 1, 0 plus A times 1, 1 equals A times V. And so A times 1, 0 is equal to 2, 0, and A times 1, 1 is equal to 3, 3. So equals to 5, 3. So A times V is equal to 5, 3. Okay. So any vector V can be decomposed.
Oh, what if V not equal to 2, 1 is equal to 3, 3, 2?
3, 2?
Yes, could you calculate that? If V equals to 3, 2.
So V equals to 3, 2. So V equals to 1, 0 plus 2, 2.
Actually, it's 2 times 1, 1 because I need to write a vector and coefficient multiply the eigenvector, right? Because only on the eigenvector direction is only scaling, not rotation, right?
So
Okay,
this time A times V is equal to
Why is 6?
because it's 2 times 3. 6.
Which 3? You need to introduce that detailedly because that 3 is a
Eigenvalue.
Yes, eigenvalue of 1, 1. Each eigenvalue have
a corresponding
a
eigenvector.
corresponding eigenvector. You need to multiply the eigenvector that multiply the eigenvalue, the eigenvector vector corresponding, right? Yes.
So it's equal to 8, 6.
Okay. So the question is, if we only know the matrix
action on these two eigenvectors, do we
can we infer its action
on any vectors? The answer is yes, because any vector can be decomposed into a linear combination of eigenvectors.
Where is the linear combination of the eigenvector in this example?
Actually, 1, 0 is P1, and then 2 is 2P2. So V equals P1 plus 2P2. So
yes, that was a combination of eigenvector. Yes, and then applying the matrix
to the eigen and to V, times the matrix A and to the eigenvector combination, and then stretch each part and then sum them.
So could you give me a congratulation or summary of how it works? The first is what?
The first
it separates how many part is separate to calculate
decomposition, stretch, recombine.
Okay, sure. Actually, it's 3 parts. And could you say it again? What you want to calculate?